The minimum ground ring conductor size is based on the National Electrical Code, or NEC, and calculated using the largest motor current. For a system with 353 full load current amps and a 53 amp largest motor, we perform the calculation 1.7 times the largest motor current, which is 1.7 times 53 amps, resulting in 89.1 amps. This requires a minimum conductor size of number 3 American wire gauge, or AUG, which is rated for 85 amps. The tap conductor size to the conveyors should be based on the current demand of the conveyors and the length of the tap conductors. However, minimum size requirements could vary if Mine Safety and Health Administration, or MSHA, requirements are being referenced. The service can be connected to the ground ring if certain requirements are met. Firstly, the ground ring is continuous and unbroken. Secondly, the ground ring is bonded to the service ground at the service entrance. And thirdly, the ground ring is of adequate size to carry the fault current. We refer to MSHA regulations for specific requirements related to grounding. The ground ring can be installed using either conduit or cable, as long as it meets the required ampacity and is properly bonded. Ensure that all metal parts of the equipment and structures are bonded to the ground ring. Given the 353 full load current amp system and the MSHA requirements, it is recommended to consult with a qualified electrical engineer to determine the appropriate conductor sizes and ensure compliance with all applicable regulations. We'll further elaborate on these points. We'll start with ground ring conductor size as it relates to the NEC. NEC Article 250 covers grounding and bonding requirements. While the NEC doesn't explicitly mandate a ground ring in all situations, it does provide guidelines for creating effective grounding electrode systems, which a ground ring can be a part of. The calculation provided 1.7 times the largest motor current isn't a direct NEC requirement for sizing the ground ring itself. Instead, it's a method to determine the minimum size of the grounding electrode conductor, or GEC, that connects the grounding electrode system, which could include a ground ring, to the service equipment. The NEC specifies various methods for establishing a grounding electrode system, including ground rods, ground plates, metal underground water pipes, and concrete encased electrodes, or UFA grounds. If a ground ring is used, it must meet specific requirements outlined in NEC 250.53. The ground ring must be buried at least 2.5 feet below the Earth's surface and consist of at least 20 feet of bare copper conductor not smaller than number 2 AWG. The 1.7 multiplier is often used in industrial settings as a conservative approach to ensure adequate grounding capacity, especially where large motors are involved. This is because motors can contribute significantly to fault currents during ground faults. Now, for tap conductor size, determining the appropriate tap conductor size for the conveyors requires a more detailed assessment. The NEC provides guidelines for sizing tap conductors in Article 240.21, but these rules are general and may not fully address the specific requirements of the conveyor system and MSHA regulations. Factors to consider include the full load current of each conveyor motor, the starting current of the motors, the length of the tap conductors, and any voltage drop limitations. The tap conductors must have an ampacity sufficient to carry the load they serve. For motor circuits, NEC 430 provides specific requirements for conductor sizing, overcurrent protection, and motor disconnecting means. The tap conductors must be protected against overcurrent, typically by a circuit breaker or fuses. The overcurrent protection device must be sized appropriately for the tap conductor and the motor it serves. Voltage drop can be a significant concern, especially with longer tap conductors. Excessive voltage drop can cause motors to overheat and malfunction. The NEC recommends limiting voltage drop to no more than 5% for motor circuits. Now, regarding the service connection, connecting the service to the ground ring is a common practice to establish a low impedance ground path for fault currents. The NEC requires the grounding electrode system to be connected to the service equipment. This connection is typically made at the service entrance through the main grounding bus bar. The ground ring, if properly installed and connected, can serve as part of the grounding electrode system. For the ground ring to be effective, it must meet the requirements previously mentioned. Firstly, It must be continuous and unbroken, forming a complete loop around the facility. Secondly, it must be bonded to the service ground at the service entrance, ensuring a low impedance path for fault currents. And thirdly, it must be of adequate size to carry the available fault current. The size of the ground ring conductor must be sufficient to handle the maximum fault current that could occur at the service. Now let's talk about MSHA requirements. MSHA regulations often have specific requirements for grounding in mining and mineral processing facilities, including wash plants. These requirements may be more stringent than the NEC requirements. MSHA regulations are designed to protect miners and prevent electrical hazards in underground and surface mining operations. MSHA may require additional grounding electrodes, specific bonding methods, and regular testing of the grounding system. It is crucial to consult the applicable MSHA regulations for the specific location and type of mining operation. Now let's consider conduit or cable. The ground ring can be installed using either conduit or cable, provided it meets the necessary requirements. If conduit is used, it must be metal conduit, such as rigid metal conduit, or RMC, intermediate metal conduit, or IMC, or electrical metallic tubing, or IMT. Metal conduit provides physical protection for the conductor and serves as an equipment grounding conductor, or EG. The conduit must be properly bonded to the ground ring conductor and to all metal enclosures and equipment along its path. If cable is used, it must be listed for direct burial and suitable for the environment. The cable must have an insulated grounding conductor that is sized according to the NEC. The cable must be protected from physical damage, such as by burying it deep enough or by using a protective covering. When discussing bonding, proper bonding is essential to ensure that all metal parts of the electrical system are at the same ground potential. Bonding creates a low impedance path for fault currents, which helps to quickly trip over current protection devices and minimize the risk of electric shock. All metal enclosures, the equipment frames, and non-current carrying metal parts must be bonded to the ground ring. Bonding can be achieved using bonding jumpers, grounding bushings, and other approved methods. The bonding connections must be mechanically secure and provide a reliable electrical connection. Now, to be more specific on the MSHA requirements, MSHA regulations for grounding can be found in Title 30 of the Code of Federal Regulations, or CFR, Part 75 for underground coal mines and Part 77 for surface coal mines and surface work areas of underground coal mines. These regulations cover various aspects of grounding, including grounding electrodes, grounding conductors, bonding, and overcurrent protection. MSHA requires that all electrical equipment be effectively grounded to minimize the risk of electric shock. The grounding system must be designed and maintained to provide a low impedance path for fault currents. MSHA also requires regular testing of the grounding system to ensure its effectiveness. The testing must be performed by qualified personnel using approved methods and equipment. Records of the testing must be maintained and made available to MSHA inspectors. It is important to note that MSHA regulations are subject to change, so it is essential to stay up to date with the latest requirements. MSHA also provides guidance and training materials to help mine operators comply with the regulations. Regarding the NEC provides comprehensive guidelines for grounding and bonding electrical systems. Article 250 of the NEC covers the general requirements for grounding and bonding, including grounding electrode systems, grounding conductors, equipment grounding, and bonding methods. The NEC also provides specific requirements for grounding different types of equipment and systems such as motors, generators, transformers, and switchgear. The NEC is updated every 3 years, so it is important to use the latest edition. The NEC is not law unless it is adopted by a state or local jurisdiction. However, it is widely recognized as the standard for safe electrical installations. Now, regarding the ground ring installation, the ground ring should be installed in a continuous loop around the facility. The ends of the conductor should be securely connected using exothermic welding or other approved methods. The ground ring should be buried at a depth of at least 2.5 feet to protect it from physical damage and to ensure good contact with the earth. The ground ring should be located as close as possible to the buildings and equipment it serves. The ground ring should be connected to all major metal structures, such as building frames, tanks, and pipelines. The connection should be made using bonding jumpers that are sized according to the NEC. The ground ring should be inspected regularly to ensure that it is in good condition and that all connections are secure. Any damage or corrosion should be repaired promptly. Now let's discuss conductor materials. The ground ring conductor is typically made of bare copper. Copper is an excellent conductor of electricity and is resistant to corrosion. The NEC requires that the ground ring conductor be at least number 2 AWG in size. However, a larger conductor may be required depending on the size of the electrical system and the available fault current. Other materials, such as aluminum, may be used for grounding conductors in certain applications. However, aluminum conductors must be sized larger than copper conductors to provide the same level of performance. Aluminum conductors must also be protected from corrosion. Now let's discuss bonding jumpers. Bonding jumpers are used to connect metal parts of the electrical system to the ground ring. Bonding jumpers should be made of copper or other approved materials. Bonding jumpers should be sized according to the NEC. Bonding jumpers should be installed in a manner that provides a low impedance path for fault currents. Bonding jumpers should be protected from physical damage and corrosion. Regarding exothermic welding is a method of creating a permanent electrical connection between two or more metal conductors. Exothermic welding involves using a chemical reaction to generate heat that melts the conductors together. Exothermic welding is commonly used to connect grounding conductors, bonding jumpers, and other electrical components. Exothermic welds are strong, reliable, and resistant to corrosion. Exothermic welding requires special equipment and training. The welding process must be performed according to the manufacturer's instructions. Regarding ground rods are another type of grounding electrode. Ground rods are typically made of copper-clad steel. Ground rods are driven into the earth to provide a connection to ground. Ground rods are often used in conjunction with ground rings to create a more effective grounding system. The NEC requires that ground rods be at least 8 feet long and 5/8 inches in diameter. The NEC also specifies the spacing and number of ground rods that are required. Now let's discuss surge protection. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning, switching transients, and other electrical disturbances. SPD are installed at the service entrance and at other locations throughout the electrical system. SPD divert surge current to ground, protecting sensitive electronic equipment from damage. SPD should be selected based on the voltage and current rating of the electrical system. SPD should be installed according to the manufacturer's instructions. Considering harmonics, harmonic currents are currents that are multiples of the fundamental frequency of the electrical system, which is typically 60 Hz. Harmonic currents can be caused by nonlinear loads such as electronic equipment, variable frequency drives, and uninterruptible power supplies. Harmonic currents can cause overheating of electrical equipment, voltage distortion, and other problems. Harmonic filters can be used to reduce harmonic currents. Harmonic filters are installed in the electrical system to block harmonic currents from flowing. Harmonic filters should be selected based on the harmonic content of the electrical system. Now, regarding the equipment grounding conductor, the equipment grounding conductor, or EG, is a conductor that connects the non-current carrying metal parts of electrical equipment to the grounding system. The EGC provides a low impedance path for fault currents, which helps to quickly trip over current protection devices and minimize the risk of electric shock. The EGC must be sized according to the NEC. The EGC must be installed in the same raceway or cable as the circuit conductors. The EGC must be connected to all metal enclosures, equipment frames, and other non-current carrying metal parts. Regarding overcurrent protection devices, such as circuit breakers and fuses, are used to protect electrical equipment from overloads and short circuits. Overcurrent protection devices must be sized according to the NEC. Overcurrent protection devices must be installed in a readily accessible location. Overcurrent protection devices must be tested regularly to ensure that they are functioning properly. Now let's talk about voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to the conductor's resistance. Excessive voltage drop can cause equipment to malfunction and can reduce the efficiency of the electrical system. The NEC recommends limiting voltage drop to no more than 5% for motor circuits. Voltage drop can be calculated using Ohm's law. The voltage drop is equal to the current multiplied by the resistance. Voltage drop can be reduced by using larger conductors or by shortening the length of the conductors. Regarding short circuit current is the current that flows during a short circuit. Short circuit current can be very high and can cause significant damage to electrical equipment. The electrical system must be designed to withstand the available short circuit current. Overcurrent protection devices must be able to interrupt the short circuit current. Short circuit current can be calculated using engineering software. Regarding grounding impedance is the resistance to the flow of current to ground. Low grounding impedance is desirable because it allows fault currents to flow quickly to ground, which helps to trip overcurrent protection devices and minimize the risk of electric shock. Grounding impedance can be measured using a ground impedance tester. Grounding impedance should be checked regularly to ensure that it is within acceptable limits. Regarding ground fault circuit interrupters, or GFCIs are used to protect people from electric shock. GFCIs detect ground faults, which are unintentional electrical paths between a live conductor and ground. GFCIs quickly interrupt the circuit when a ground fault is detected, preventing electric shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas. Now let's talk about electrical safety. Electrical safety is of paramount importance. Electrical work should only be performed by qualified personnel. Electrical equipment should be properly maintained. Electrical hazards should be identified and corrected promptly. Personal protective equipment, or PPE, such as gloves, safety glasses, and arc flash suits should be used when working on electrical equipment. Electrical safety training should be provided to all employees who work with or around electrical equipment. Continuing education and professional development are essential for staying current with the latest electrical codes, standards, and best practices. Participation in industry conferences, workshops, and seminars can provide valuable learning opportunities and networking opportunities. Certification programs such as those offered by the International Association of Electrical Inspectors, or IAE, and the National Fire Protection Association, or NFPA, can demonstrate competency and enhance professional credibility. Consulting with experienced electrical engineers and other qualified professionals can provide valuable insights and guidance on complex electrical issues. Collaboration with industry experts can help ensure that electrical systems are designed, installed, and maintained in a safe and efficient manner. By working together, electrical professionals can promote electrical safety and protect people and property from electrical hazards. Regarding documentation, maintaining accurate and up-to-date documentation is essential for the safe and efficient operation of electrical systems. Documentation should include single-line diagrams, panel schedules, wiring diagrams, and equipment specifications. Documentation should be readily accessible to qualified personnel. Documentation should be updated whenever changes are made to the electrical system. Regarding inspections, regular inspections of electrical systems are essential for identifying potential problems and ensuring that the systems are operating safely. Inspections should be performed by qualified personnel. Inspections should be conducted according to established checklists and procedures. Inspection findings should be documented and corrected promptly. Now let's discuss electrical codes and standards. Electrical codes and standards are developed by organizations such as the NEC, the Institute of Electrical and Electronics Engineers, or IEE, and the American National Standards Institute, or ANSI. Electrical codes and standards provide guidelines for the safe and efficient design, installation, and operation of electrical systems. Electrical codes and standards are constantly evolving to reflect new technologies and best practices. It is important to stay up to date with the latest electrical codes and standards. Also, you will want to verify your work by using a multimeter to measure voltage, current, and resistance. Clamp meters can measure current without disconnecting conductors. Insulation testers can measure the insulation resistance of conductors and equipment. Ground resistance testers can measure the resistance of the grounding system. Power quality analyzers can measure voltage, current, harmonics, and other power quality parameters. Thermal imagers can detect hot spots in electrical equipment.